Hello everyone. Continuing with our discussion of different functional forms, this video looks into quadratic functional forms. So these are regressions where a particular regressor enters the model both with power 1 and with power 2, and hence the term quadratic functional form. So here's an example where we have dependent variable y and a regressor x. And if x enters so in a quadratic model, we'll write the model as y being a function of y equals beta naught plus beta 1 x plus beta 2 times x squared. So the reason these models are actually interesting is that when you want to understand partial effects, that is, for a 1 unit change in x, what is the corresponding change in y? Those partial effects, or what we call marginal effects, now start taking on a slightly different interpretation. The marginal effect of x on y will actually depend on how much, on the actual value of x. So bear with me for a few seconds, and I'll give you an example, and that will make sense. So if my regression model is given by beta naught plus beta 1 x plus beta 2 x square plus u, if I were to take dy by dx, which is the change in y for a unit change in x, I'm going to get beta 1 plus 2 times beta 2 times x. Earlier, when we did dy by dx, our answers were just constants, just the beta coefficients. But now, you notice that your partial effect is now dependent on the value of x. For a particular, if you plug in different values of x, you're going to get different marginal or partial effects. And that's the difference here. So let's look at an example. And I'm going to very quickly change the color of my pen. Right. So if we were regressing wages of people on the experience that they have, and suppose we want to build a quadratic model here where experience enters the equation quadratically. In that case, we'll include experience and experience square as regressors in the model. And we've run this regression using OLS, and the coefficients and standard errors are given to you. If we were to go ahead and figure out what's the effect of an additional year of experience on this person's wage, on wage in average. So let's go ahead and figure that out. So I'm actually doing change in wage by change in experience. And that's just going to be 0.298 minus 2 times 0.0061 times experience. I'm just using principles of single variable calculus to get this answer. And that is what you see here. So an additional year of experience, the effect of that on wage is a function of how much experience the person already has. So by plugging in different values for experience here, we can actually figure out what the effect on their wage is. So when the person just has 1 year of, if they're just starting out, experience is 0. So if they gain any more experience, their wages are going to go up by 0.298 or roughly 30 cents. Once they've worked for a year, if they're working for a second year, then they now have an experience of 1 year. So if you plug in experience equals 1 into that expression and compute the number, the answer turns out to be roughly 0.29, meaning when the person already has a year of experience, gaining an additional year of experience would increase their wages by 29 cents. Now, suppose we keep changing these numbers. Suppose this person has 5 years of experience. What's the effect of the 6th year of experience? Well, it turns out the 6th year increases wages by $0.237. If they keep working, say for 15 years, then the 16th year of experience will increase wages, but only by $0.11. So notice how the change in wage actually started out at 30 cents and now came to 29 and then to 23, roughly 24, and then 11 cents. So here, we're saying that the effect of experience on wages is increasing, but at a decreasing rate. And that should remind you of concave functions and parabolas, which we use to describe concave functions. And if you were to recap all that you learned in math, when you have a concave quadratic function, the increase at a decreasing rate is just given by the signs of the coefficients attached to the linear and the quadratic terms. So you have a plus here and you have a minus there. And that tells you it's increasing at a decreasing rate, and we have a concave experience profile. So if I have wages here and experience here, this just tells me that, with no experience, we start off at 3.73, but after that, my wages are going to increase at a decreasing rate. And because it's a concave function, it may actually tip over. So does that mean that after a certain period of experience doesn't matter to wages? Okay, so let me go over that again. We now have established the fact that wages increase with experience, but at a decreasing rate. So we have a concave profile for experience. And using principles from just the geometry of parabolas, we can figure out where this turning point happens. Or if you were to just use calculus, you just have to find the point of maximum of that function. And at the maximum, if you put a first derivative there, that's going to be 0. The slope of the tangent at the maximum is going to be 0. And delta wage by delta experience is the slope that we're talking about. And that is just beta 1 plus 2 times beta 2. And if you set that equal to 0, 2 times beta 2 x, if you set that equal to 0, you'll be able to figure out the value of x where this tipping point happens. And the formula here in this slide just comes from the geometry of parabola, but if you want, you can look up that formula, or you can just use intuition from calculus. So in this example, turns out that that tipping point happens at 24.4 years of experience. So does that mean that up to 24 years of experience, your wages are increasing at a decreasing rate, but after that they start falling? In that case, does it mean that 25 years of experience is actually bad for this person? Well, we are liable to make such an interpretation, but we should just be a little bit cautious there. And it need not necessarily mean that return to experience becomes negative after those 24 years. So if you look at your data sample beyond this point, right, to the right of 24 years, if there are very few observations in the sample that fall in that category, then you don't have to worry much. There's just a very small data coming from that chunk, which is, and so we don't have enough observations beyond 24 years to very few cases beyond 24 years. So it doesn't actually matter to think about what 25 years of experience would mean. But in this example, in this data set that was used for this regression, about a third of the data, about 28% of the observations have an X value that is greater than 24. About a third of my data set has individuals whose experience exceeds 24 years. So that is quite a sizable chunk. So in that case, we have to be really careful in how we're interpreting these results of 24 being a maximum, a peak experience period. It is very likely that our model has some omitted variables. We're not accounting for enough explanatory variables to talk about, to describe wages. Remember, we've only included experience. There could be several other things like education, inherent IQ levels, or where the person is living, and so on and so forth, that could explain wages. So in this case, we have an omitted variable problem, most likely. Let's look at another example. So we're now looking at quadratic forms in regression models that have logged variables as well. So we have housing prices, depending on pollution levels, distance from a certain headquarters, number of rooms in the house, and so on. So we're now going to focus only on the dependent variable, and notice that the number of rooms enters the regression model in quadratic terms. So you have a rooms and a rooms square in your model. So if we go ahead and compute the partial effect of rooms, that is, if we want to see what's the change in log price when the number of rooms is changing, all I have to do is just take change in log price divided by over change in rooms. And if I just use the principles of calculus, my results are going to be minus 0.545 plus 0.124 times rooms. That is, if I'm looking at how the change in the number of rooms affects prices, that change actually depends on how many rooms the house actually has. Does it have one room or two rooms? So where exactly are you looking at that change from? That's what we have to be careful about. So here is an example where we have something which has a convex profile. So notice that the coefficient on room square is actually positive. And you see this number, once you graph this, this will start making a lot more sense. So we're actually talking about the more rooms the house has, an additional room will increase the price that much more. So let me pare back what I just said. Suppose there are very few rooms in the house. Suppose there is just one room in the house. If we increase the number of rooms to say 2, in that case, the change in the price is just going to be minus 0.545 plus 0.124 into 1. So we are at one room and we are increasing it by one more room. So the marginal effect is given by this number. And this is actually going to be less than 0. So which means that if I just have one room in the house, if I have a second room, that is actually going to suppress my house prices. Or rather, more rooms are associated now with lower prices. That doesn't quite make sense, right? We're going to have a very similar interpretation here as well, like we did with the similar nuance here, like we did in the earlier example. So here is a model where rooms actually has a convex relationship to log of prices. We start off at a particular value, and until we get to a certain number of rooms, turns out that more rooms are actually suppressing house prices. So you could try that in the previous case by looking at minus 0.545, let's say 0.124 into 2. So you're at 2 rooms and increasing to a third room, so on and so forth. So until you get to a certain turning point, a critical point, which in this example is about 4.4 rooms, which again is just that point where the slope of the tangent to that curve is 0. You can go ahead and find that out using calculus. At about 4 rooms or so, once you cross the threshold, every additional room that you have is actually going to increase the house prices. But before that, house prices are falling. And that is not a very realistic story that we hear. So what we do is we go ahead and look at the size of the data to the left of that turning point. Well, it turns out that we only have 1% of the observations. Only 1% of houses in our data set have lesser than 4 rooms. So it's not a very important thing for us to be concerned about houses with less than 4 rooms. So our primary interest now focuses to what happens beyond 4 rooms. So, and we have a convex relationship, meaning the house prices are increasing at an increasing rate with the number of rooms. To give you a numerical example, suppose the house has 5 rooms, but we're now increasing to and getting a 6th room. In that case, the change in prices is given by this formula, and that's about a 7.5% increase in price. Suppose you have 6 rooms already and you want to move to a 7th room, you calculate this expression, and that's a whopping 19.9% increase in price. So you see how that beyond a threshold, there's a convex relationship. It starts increasing at an increasing rate. And we have heard of larger mansions and villas selling for a lot more than just a 2-bedroom apartment. So this is a fairly reasonable thing. So when you have such scenarios where X and Y are related in a quadratic sense, a quadratic regression model is the most appropriate in those scenarios. So I will just do one more thing and stop this video here. A quadratic functional form also lends itself to cases where you have log-log models. So for example, in this case, if pollution enters the model quadratically, but it's all log transformed in this case, if I want to look at what's the percentage change in price for a percentage change in pollution, okay, which is just taking the derivative that you see there on the slide. The answer now depends on how much of pollution there is. So depending on how much of pollution there is, for a percentage increase in pollution from that starting point, your percentage increases in price will vary, changes in price will vary correspondingly. So that's the utility of having quadratic forms. And we can actually expand the linear regression models to have more polynomial terms. You could have cubic functions. You could have functions where the regressor is raised to power 4 and so on and so forth. So I will stop this video here, and in the next one, I talk to you about interaction terms. See you there.